So welcome to the workshop. Today we'll be going over scientific notation, significant figures, measurements, calculations, and dimensional analysis. And so for our first section is going to be scientific notation. A quick little recap. Scientific notation is typically used to help report a large or a small number in a way that is both understandable and readable to others. So we see this first example. We have 15 billion. That has like 9 zeros. It can be quite cumbersome to write 9 zeros every time you do a calculation, or for another reader to look at it. It's very annoying to have to read and count every single zero just so they can understand what number you're referencing to. So instead, what we can do is we can condense 15 billion into a small three-digit or decimal that is only a few digits long. So we can see this decimal point right here. We can move it 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So we can represent 15 billion as 1.5 times 10 to the 10. Here we have a smaller number, is going to be 0.000000018. We can represent this in scientific notation as 1, 2, 3, 4, 5, 6, 7. So we can represent this number as 1.8 times 10 to the negative 7. So there are multiple parts to a number in scientific notation. There's a decimal part here in orange. It's going to be a number between 1 and 10. You typically don't write it as anything outside that range. It could be a negative number though. On the red part here, we have the exponent and the exponent part. So it's always going to be base 10, and the exponent is always going to be a integer number. So you don't want to put a decimal in the exponent. Otherwise, it's not really scientific notation. All right, so we'll practice. You can pause the video and try these out on your own. It's going to be writing these following numbers in scientific notation. And then afterwards, you can convert these scientific notation numbers into standard form. And so here for number 1, we have 16 million. What I can do here is I'm going to count the decimal place and move it all the way over such that the number is between 1 and 10. So I'm going to move this decimal place 1, 2, 3, 4, 5, 6, 7. And so this is going to be 1.6 times 10 to the 7. Number 2, we have 0.00035. So this is going to be a number that's smaller than 1. So I'm going to move this decimal place over 1, 2, 3, 4. And so I move the decimal places 4 spaces to the right. So we can represent that number as a negative exponent. So I'm going to write 3.5 times 10 to the negative 4. This next number, we have 128 billion. So I'm going to put the decimal place here, and then I'm going to move it over to the left all the way until I get to a number between 1 and 10. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is going to be 1.28 times 10 to the 11. And for number 4, we have 0.08. So this is going to be represented as 8.0. And I'm going to move it to the right, 1, 2. So this is going to be 8.0 times 10 to the negative 2. So now backwards, we're going to convert these scientific notation numbers into standard form. We have 1.8 times 10 to the 3. So what I'm going to do here is I'm going to write 1.8 and then move the decimal place to the right 3 times. So 1, 2, and then 3. And I'm just going to put zeros in between each part of the decimal place. And so this is going to be represented as 1800. We have this next number, 2.4 times 10 to the negative 4. So I'm going to write 2.4. And then I'm going to move it to the left 4 places because we have a negative 4 in the exponent. So it'll be 1, 2, 3, 4. And so 2.4 times 10 to the negative 4 can be represented as 0.00024. This next number, 1.65 times 10 to the 7. So I'm going to write 1.65. And I'm going to move it over the decimal place to the right 7 places. So I'm going to do 1, 2, 3, 4, 5, 6, 7. I'll put the decimal here and then put all these zeros in between. And so this number is representing 16,500,000. And finally, number 4, we have 9.99 times 10 to the 3. I'm going to write 9.99. And I'm going to move the decimal place to the right 3 places. So 1, 2, and 3. And so this is going to represent 9,990. And so for our next section, we have significant figures and recorded measurements. So it's important to remember that the accuracy of any reported value is going to be crucial in your calculations. So here we have this ruler right here. There's not a lot of tick marks on this very first one, but the second one has some more tick marks, and then the third one is much more detailed than the second one. So we only record measurements such that the last digit is uncertain and is estimated. So if you look at this first ruler right here, I could not be confident that this is actually 20 or 30. It could be 10 or 40, depending on how far you may have seen it or how small this measurement could have been. So we measure that we have an uncertain number between 20 or 30 for this first one. So I'm just going to write to the right here. I'm just going to write 20 centimeters. But this next one, the second ruler right here, you can see that it's between 20 and 30, but we're not really sure about that final digit in between. So we're just going to have to make a reasonable guess as to what number that's going to be. So this could be, you can see it probably as 22, 23, 24, somewhere around there, but it's probably less than 25 centimeters, just like right around here. So I'm just going to say maybe 22 centimeters. And then this third one, there's a lot more tick marks in between the 20 and the 30, so we can actually count it a lot more precisely. So we have 1, 2, 3. So it's between 23 and 24 centimeters. It's actually right now. It's between 22 and 23 centimeters. So we can say it's about 22 centimeters, but we're unsure of where that last decimal place is. So we can just take a guess, and since it's really small here, the precision or doesn't really matter. by as much, but you still want to make a reasonable guess. So I could say this is probably like 22.4 or 22.5, anywhere around there is considered a reasonable measurement. So you can see here, we only record the measurements such that the last significant digit is uncertain and estimated. So we can see this 20 on this first measurement right here. That's the only uncertain or estimated value right here. This second ruler, we only have two significant figures, so we can see this final digit, the 2 and the 22, or the last digit of 22. Is going to be, this one is significant because this is the last digit is quite uncertain, or we're estimating that number. And finally, for this third one, we have 22.4. So we know that it's definitely between 22 and 23, but we're not actually sure if it's between, if it's 22.5, 22.3, 22.6. So we're just going to say that this 4 in the decimal place is uncertain or estimated. So a quick little recap on conditions for what is a significant figure. So the condition, we have non-zero digits. Those are always going to be significant. Zeros between non-zero digits. So this is going to be like this number, 708. So there's a 0 between these two non-zero digits. So that's going to be considered significant. This first example is going to be like, we'll just put 85. So these are both non-zero numbers. They're both going to be significant. Leading zeros, so this actually isn't significant. So, for example, this number is 0.005. So these zeros in the front, they don't really tell us anything about how precise that last measurement is. So they're not actually significant. We know already that this part is going to be estimated, and we already know that these are like kind of like known or exact values. This next one, trailing zeros in a decimal. So, for example, we have this number. We'll just put 3,000. And then if I put a decimal here, this is considered a trailing zero. Because there's a decimal here, we are actually indicating that every single zero is going to be significant. Except for the leading zeros, but there's no leading zeros in this particular example. And then finally, just trailing zeros. If you don't include a decimal, it is actually ambiguous. So if I just put, for example, 3,200 right here, you could say that there might be 4 significant figures because there's this 1, 2, 3, and 4. But you could also say that because we don't follow the trailing zeros, we only count these two, you might say that there's also 2 significant figures. So a way to work around that is instead we're going to represent 3,200 in scientific notation. So we can put this decimal here, and then we can put 1, 2, 3. And so in order to avoid ambiguity, we can write these trailing zeros as 3.2 times 10 to the... This number would have 2 significant figures. Now, if you were to write this as 3.20 times 10 to the 3, this would be 3 significant figures. And finally, if we were to write this as 3.200 times 10 to the 3, Since it satisfies all the other conditions for what is considered a significant figure, this would be 4 significant figures. All right, so more practice. So determine the number of significant figures. You can go ahead and pause the video and try this out on your own, and then I'll go over these problems. So for this first one, 58.31, there are 4 significant figures, and that is because there are 4 non-zero digits in the number. So it's going to be 4 SF. Number 2, we have 0.00250. So we have these leading zeros right here. All 3 of these are not going to be significant. And then we have 250. The 0 at the very end is considered significant because there's a decimal in the number. So this would be counting as 1, 2, 3. So 0.00250 has 3 significant figures. Uh, 2.7 times 10 to the 3. This is just going to be 2 significant figures because there's going to be no zeros in this number, and every single number is an odd zero digit. So there's going to be 2 significant figures. Number 4 is 0.01. So these leading zeros are not going to be significant. And so that just leaves us with 1. So this is just going to be a 1 significant figure. Number 5, you have 0.500. There's going to be a leading zero right here. There is a decimal in this number. And then there are trailing zeros at the end. So these 3 trailing and these 2 trailing zeros are going to be significant, which gives us a total of 3 significant figures. And finally, we have 2100. This is going to be ambiguous. So we could actually write this in scientific notation to avoid ambiguity. So we can write this as 2.1 times 10 to the 3. This would give us 2 significant figures. We can write this as 2.10. And that's going to be 3 significant figures. And we can also write this as 2.100 times 10 to the 3. And then that'll be 4 significant figures. So this next problem, what does the following measurement read? And try to provide the appropriate number of significant figures. So go ahead and try and read this measurement. And yeah. So if you look at this graduated cylinder right here, you can see that there's a meniscus here, which is basically just this little dip inside the cylinder. And we're always going to read the lowest point of the liquid inside. So if we count this graduated cylinder, we have 20, 21, 22, 23, and then 24. So we can read this, and we can report this measurement as 24 4, and there's no units on this one, so you don't need to report units on this particular example. So I can record this number as 24.0. Another possible answer you can write is 23.9 or 24.1. And these are all going to be valid answers because we're not actually sure about that final digit. It's always going to be estimated. Moving on, we have significant figures and using them in calculations. So in short, for multiplication and division, the result should always carry the same number of sig figs as the number with the fewest sig figs. And as for addition and subtraction, the result should have the same number of decimal places as the number with the fewest decimal places. So in this first example, we have 89.665 times 0.12. So I'm just going to write, this has 5 significant figures here. Uh, 0.12 has 2 significant figures. And then I'm just going to punch this into my calculator to make sure that the calculation is correct. And so the answer is about 10.759. It seems right. And then since we have 2 significant figures, we only record the first 2 significant digits in that number. So if this is going to be the second significant digit, we can always check for rounding right here. So this is 10.77 rounds up. And then this becomes just 11. Next, we have addition and subtraction example. So we have 5.74 plus 0.823. So what I like to do for these addition and subtraction significant figure calculations is I like to write them like this and then line up the decimals. So I'm going to write 5.74 plus 0.823. And then I'm going to draw a line right where the place where the least significant decimal place is. And then I'm just going to carry out the calculation as normal. So I can put this as 7. Oh, this is addition. So this is 3. This is 6. This is 5. And then this is going to be 6. So the answer before we take into account significant figures will be 6.56 because this is going to be the least amount of decimal places in the number. And then when we record our number, we only keep these 3. So that's how the answer becomes 6.56. So what if the calculation has both? So the calculation has both addition, subtraction, and multiplication and division. We're mostly just going to follow PEMDAS, and then we're going to determine the appropriate number of significant figures first, and then we're going to complete the remaining steps. So we have this example right here, 3.489 times the difference between 5.67 and 2.3. So following PEMDAS, we have parentheses. So we're just going to evaluate this part of the problem first. So we do 5.67 minus 2.3. We're going to get 3.37. And so this is going to be the first part of the equation. And then the next part, we're going to do the multiplication part. So we're just going to do 2.49489 times 3.37. Keep in mind that I have not rounded any intermediate calculations. You never want to do that because it's going to give you a very inaccurate answer. So I'm just going to punch this into my calculator. And it's going to get me 11.7579. And so we're going to have to take into account significant figures now. And so since this is going to be the amount of significant figures that we're going to be taking into account, this subtraction part, we're only going to have a total of 2 significant figures after we subtract these 2 numbers before we do multiplication. And then after we do the multiplication, there's only 2 significant figures in the answer. So we're going to just only record the first 2 in our result. So then we're going to check for rounding here. This is going to be a 0.7, so this is going to round up. And then that's going to get us our answer of 12. All right, so practice. Try and do these problems on your own. Pause the video, and then I'm going to try and go over them and see if you got the right answer. All right, so for number 1, we have a division problem. There's going to be no mixed operations or anything in here. So we're just going to do 5.892 divided by 6.10. I'm going to put this in my calculator. And that gets me an answer of 0.965. And now just put out one more digit here. And so this is going to be a total of 3 significant figures because this number has 3 significant figures. So our answer is actually going to be 0.966 because this is going to be the significant decimal place, and then we're going to check for rounding, and this rounds up, and we get this answer. The next problem, we have 1.10, so I'm going to put this in the calculator, times 0.512 times 982.301 times 0.005, and then divided by 3.4. And so we're going to get an answer of 0.81357. And since there's only going to be a total of 1 significant figure, we're only going to record 1 digit. And so then our answer is going to be, in this case, it's just going to be 0.8. The next problem is going to be 0.987 plus 125.1 minus 1.22. And that's going to give us an answer of 1.24867. And so we're going to check the number of decimal places. And you see here that the 125.1 only has one decimal place. And so our answer is only going to record that one decimal place from here. And since there's no, it's not going to be rounded up, our final answer is just going to be 1.2. Next, we have 0.765 minus 3.449 minus 5.98. So I'm going to put this into my calculator once again. And the answer is going to be negative 8.664. And since there's only going to be a total of two significant decimal places because of this 5.98, we're only going to record two significant decimal places in our answer. So we're going to get negative 8.66. Finally, for number 5, we have 19.667 minus the product of 5.4 times 0.916. I'm going to solve what's in the parentheses first. And so if we solve what's in the parentheses first, we're going to get 4.9464. And then we're going to carry our subtraction afterwards. And so because there's only going to be three significant decimal places in this, oh wait, sorry about that. This is actually going to be two significant decimal places, or two significant figures, because this multiplication step right here has a total of 2. So we're going to carry out the operation. I'm going to put in my calculator. So I got 1.47 times 10 to 1. So this is going to be 14.7. And then we only take two significant figures here, so the answer is going to be 15. Now moving on to the next section, we have problem solving and dimensional analysis. So the general formula for dimensional analysis is just going to be the given unit times the desired unit over the given unit, and then ideally these units will cancel out, and then you are left with your desired unit. And so conversions between units do require dimensional analysis to solve. This is going to be a skill that you're going to be using pretty much throughout all of chemistry. So for example, here we have how many centimeters are going to be in 17.6 inches. So we can see here, this is a setup right here. We have the inches on the bottom, and then inches on the top is going to cancel out. And then what we're left here is the centimeters. So our answer is going to be in centimeters. And just keep in mind of significant figures when you're doing these calculations. So we have a total of 3 significant figures in our answer. So breaking down this equation, we have the given right here. Over here, we have the conversion factor. And then over here, we have the answer. And so some general pointers when you do dimensional analysis, what you always want to think about the units that cancel. So your answer should only contain all the units that were not canceled, pretty much. If you have some leftover units in your work or when you're doing calculations, it probably is an indicator that you may have made a mistake. And see, another thing is you always want to keep in track of your significant figures. Also keep in mind that conversion factors don't actually count for significant figures because they are considered exact values. So you can kind of treat them as like having an infinite amount. You always want to write your units in your calculations. This is probably the easiest way that I found to avoid making simple errors whenever you're doing your calculation, and also makes it easier for other people to read your work and get an understanding of uh, how you're getting your numbers. And four, we have remember that there's going to be more than one way that you can represent a conversion factor. So we see this one right here as 10 to the negative 3 meters per 1 millimeter is actually the same thing as 1 millimeter is equal to 10 to the 3 millimeters. So this is something that I often encounter and is kind of hard to explain other than to think about it. Doesn't make sense physically. So sometimes I might see someone write, or I might see myself accidentally write 10 to the 3 meters is equal to 1 millimeter. And that doesn't really make any sense because a meter is going to be much larger than a millimeter. But when you write the conversion factor like this, you're saying that you need many, you actually need 1,000 meters for 1 millimeter, which is, it doesn't make sense. It's definitely not true. So you always want to think about your answer. Does it make sense? And finally, we have some practice. We're going to be doing some basic conversions. Some of them is going to be using density, and we can use density as a conversion factor. So go ahead and pause the video and try these on your own. And so for this first one, we have 194 centimeters to inches. So I have the given unit is going to be 194 centimeters. The conversion factor is 2.54 centimeters is equal to 1 inch. So I can put this conversion factor down here. And then if we put this into our calculator, we're going to get 194 divided by 2.54. So we're going to get an answer of 763, I'm sorry, 76.37 inches. And since we only have 3 significant figures in this problem, in the given, we're only going to record 3. So then we're going to do that. And then we're going to check the next decimal place to see if we're going to round our answer. And because this is going to be a 7, it's going to round up. So we can record our final answer as 76.4 inches. The next question is 7.8 kilometers to miles. So the conversion factor for miles is going to be 1 kilometer is equal to 0.6214 miles. So I'm just going to write down a given. And we want the units to always cancel out. So I'm going to put the kilometers on the bottom. And then the conversion rate is that's going to be equal to 0.6214 miles. And then if we put that into our calculator, we're going to get an answer of 4.846. And then if we take into account significant figures, we're going to have 2 in our given. So we're going to record only 2 in our answer. So we can report this number as 4.8 miles. And continuing on, actually for number 2, there's more than one way you can represent this conversion factor. So I'm going to write another one up here. So what we can actually also do as an alternative route is we can write 7.4 kilometers and 7.8 kilometers. And since there's more than one way you can represent this conversion factor, you can also represent it as 1.609 kilometers is equal to 1 mile. And so this is just a different way to represent what is essentially the same thing. And so if you put that in your calculator, ideally you will get the same answer. And so I'm getting 4.847. And if we take into account the significant figures, we're also going to get 2 significant figures in our answer. So we're also going to get 4.8. This next one, number 3, we have 0.825 meters to millimeters. The conversion factor is going to be 1 meter is equal to 1,000 millimeters. So I'm going to write down our given. So we have 0.825 meters. And then the conversion factor is that 1 meter is equal to 1,000 millimeters. And then if we multiply this, or if you want to put it into a calculator, we will get an answer of 825 millimeters. Because the units will cancel out from the meters and the conversion factor, giving us only the millimeters as our final units. And then if you want to think about it, this answer makes sense. So we have a number that is meters is going to be a lot larger than millimeters. So ideally, you're going to want a lot of millimeters to be equal to 1 meter. So our answer should have more millimeters in terms of the number compared to the number that you see in front of the meters. Because the millimeters are going to be a much smaller unit overall. So yeah, this answer makes physical sense. Number 4, what is the mass in grams of 50 milliliters of ethanol? And so ethanol has a density of 0.789 grams per milliliter. And so we can use density as a conversion factor. So I'm going to write down our given. We have 50 milliliters. And so ETOH is just ethanol. And so our conversion factor is that we can use density. So what we want here is we want our milliliters to cancel out. So we want to put milliliters in the bottom. And then what we're looking for is the mass in grams. So we can put the mass or the density, the 0.789 grams. And then if we cancel it out, we get a total or a final unit in grams. And so the final answer is going to be 39.45 grams. So this is going to be our final answer. We're going to take into account the significant figures here. This one is not really well written. I would say if I were to put this question again, I would put a decimal here, just to indicate that there's actually 2 significant figures, because this number is quite ambiguous. So if I were to put 2 significant figures here, then we'll want 2 significant figures in our answer. So this is going to be 39 grams of ethanol. And so finally, our last question is, what is the units of P in the following equation? And so a little hint is we want to cancel out as many units as possible. So if you look at this one, we have P is equal to, and then we have this huge fraction right here. So this is going to be a unit called moles. Moles times liter atmospheres over mole times K again, all divided by liters. So we're looking for the units of P. And so if we do some canceling, we can see that this mole cancels out here. This Kelvin K cancels out here too. We have a liters in the numerator and a liters in the denominator, so this also cancels out. And what we're left at the end is just atmospheres. And it makes sense because pressure is a unit that is measured in atmospheres or mmHg. There are multiple units of pressure, but it makes sense that we got atmospheres as one of our possible units. And so that basically concludes the workshop. I'd like to thank you all for listening. And if you have any questions, you can always schedule for tutoring. If you haven't joined already, we have a virtual STEM center on Canvas, and you can self-enroll on there, so you can also book appointments on there. And if you have any questions about tutoring or regarding the Natural Science STEM Center, you can contact us at naturalsciencecenter@scta.edu, or you can meet us on social media at pcc.stem or the Nat Sci STEM on Facebook. So yeah, that's pretty much it.